All right, it's 11:15. I think we'll get started. So welcome to the end of the last week of MATSE 202. Again, you have a homework assignment due tonight. Get that in, just like any other homework. It won't take you very long. Make sure you do the PLAs, and we won't have a PLA for Monday because there's no class. So don't email me about class. Don't ask if there's a video posted. Please make sure to remember MLK Day, and then enjoy the rest of the day with no classes. It is a work day for me. And so if you want office hours, or if you have some questions or want to make an appointment, that's fine. Otherwise, just no formal class. We'll pick it up again on Wednesday. And after this lecture, we only have 2 more lectures before homework 1 is due. And so now is a good time to download homework 1, take a look at it, start to think about what questions you're going to have to answer. Think about what you might know on homework 1 and what you don't know on homework number 1, so you can start to think about in the lecture how we're going to get to it. I'm going to try and cover everything that you need for homework number 1. If I don't, ask me a question before or after class, ask a question in class. That's a good way to get the information you need. And remember, the last office hours is on Thursday, which is really when I want to answer all the questions that are needed for the homework. And I'm not going to be very available on Friday evening or late Friday afternoon when you're finally getting around to the homework. You know, there's no guarantee that I'm going to answer your questions then, especially after 5 o'clock on Friday afternoon. Okay, that's it. Make sure that that's all set. And we're getting into the swing of things in terms of real polymer stuff and starting into the meat of the course. Oh, what I wanted to say is that the book is a great resource for the homework and for things that I don't necessarily cover in depth. And so remember to take a look at the book if you have a question about something, because oftentimes the answer is in there. And in the office hours, what I'll do is I'll say, okay, we covered that on lecture 3, slide 7, and here it is in the book. And so don't be shy in terms of getting familiar with that textbook. It's really easy to read. It's got lots of information. It's got a good index. And remember, the syllabus has all of the book sections in it that relate to what we're talking about. So it should be pretty easy to find information in the book. All right. Any questions or comments before we get started? No? All right. So the most important thing when we're starting to write chemical structures for polymers is don't forget the rules. Don't forget there are 4 bonds to carbon, 2 bonds to oxygen, 1 bond to hydrogen. You know, polymers, there's some weird nomenclature like the parentheses, and the end groups are kind of unknown unless we really focus on the end groups. But don't forget the fundamentals. They're still organic molecules, and so we want to pay attention to that. And also in terms of organic molecules, don't forget the geometrical structures that you learned in organic chemistry. And so make sure that you keep your eyes on things like that. And also, finally, polarity. Polarity, make sure you know what's polar, what's not polar, why something might be polar or not. And so, you know, all of those concepts that you've learned previously in chemistry classes still work for this class. And so we left off about here last time. And again, going from an organic molecule that you recognize like acetylene, right? That's easy to figure out. So this is the small molecule acetylene. And we can call this a monomer. 1 unit, monomer. And then to get polyacetylene, all we have to do is turn acetylene into a polymer somehow. And so there are some clues, and we're going to talk about the clues for different ways to make monomers into polymers. But one of the clues is a double or triple bond. And so when we have polyethylene, and I'm going to do shorthand, depending on your level of expertise, you can do shorthand or longhand, but you just need to demonstrate to me that you know what's happening. So remember that we take the double bond and we take an electron from one of the double bonds and bring it to each side. That gives us a half covalent bond on each side of the carbon. And then if we want to be perfect here, this is a drawing that goes from ethylene monomer to polyethylene polymer. And it's exactly the same process for polyacetylene. And so this is where counting and this is where accounting for the electrons really matters, because you're only going to take one electron one way, one electron the other way. And now you have polyacetylene. We can put that on there and say, how many hydrogens are on there? 1, 2, 3, 4 bonds to carbon. 1, 2, 3, 4 bonds to carbon. I'm all set. I don't want to put any more hydrogens on there. I didn't bring in any new hydrogens. I didn't get rid of any hydrogens because, of course, polyacetylene has some hydrogens on it. But now the difference is that through our accounting, we took one covalent bond and we made our polymer connections, those half covalent bonds on each side, but we still have the double bond between the carbons. And that's really important. You might be tempted to just say, well, I really know this structure, so I'm just going to write this down. And that would be wrong for the acetylene monomer because you've gotten rid of another double bond somehow and some more hydrogens came in. Or you might be tempted to say, well, maybe I should just drop some hydrogens on there because I've seen that a lot. That would be wrong because now you have 5 bonds to carbon. And that oftentimes does not work, even though there are such things in advanced organic chemistry for pentavalent carbon. Yes?
Wouldn't there be 5 bonds? Because 2 bonds here and 2 bonds there.
5 bonds. So remember, 1, 2, 3, 4. So there's only 4 covalent bonds around that carbon. 1, 2, 3, 4. There's only 4 bonds around that carbon. 1, 2, 3, 4. 1, 2, 3, 4. So there's no 5 bonds to carbon in any of these structures as I've shown here. Good with that? Yeah. So this is critical because this is the easiest demonstration of this. If you can't get ethylene and acetylene, you're really going to struggle when we start putting all sorts of R groups on there. One sec. Because a lot of polymerizations that we'll talk about are polymerizations like this. And this is all you'll see. And so you go from this monomer and we open up this double bond, and oftentimes I won't write the half arrows, and you'll go to something like this, and you know that there are hydrogens here, hydrogens here, hydrogens here, and now you start to have a lot of different polymers that you can make based on those R groups. So we're not always going to have hydrogens, but you know from the nomenclature of organic chemistry that we can have R1, R2, R3, and we can define those later. So make sure that you can work with this page and make sure you understand where all the hydrogens are going, where all the electrons are going. You can push some arrows and you understand how we go from monomer to polymer, because this is key. And the important fact is we only pushed electrons. We didn't get rid of any atoms. We didn't gain any atoms. None of the atoms actually moved. We just pushed electrons around. One sec, there's a hand up back here first. Yeah.
Yeah, but you just said that that doesn't lose any atoms. What about the hydrogens? Don't they?
Remember, in shorthand, hydrogens are here. Hydrogens are here. Hydrogen is there. Because even monomers, right, have 4 bonds to carbon. And so I want you on your homework to really get familiar with drawing all those hydrogens so you can do the accounting in lecture. Because I'm a polymer professional, sometimes I'll do a shorthand. And I will assume that you're with me on you have to fill in the hydrogens in order to get 4 bonds to carbon. Keep going. Yeah.
My original question was more though, so there's a double bond there between the carbons. How do the hydrogens arrange themselves in like a cis or like a trans way geometrically?
That is a that is a very good question, and we're going to cover cis and trans in a second, because when we have double bonds still in the polymer, you can have cis and trans isomers. We will get there. Yeah, just keep that in mind. Yes.
So far, what I've noticed so far is that we've only mostly been talking about just linear, like linear molecules when we talk about polymerization. So how did it change for tetrahedral archical planar geometries or hexagonal?
So remember that the molecular geometry is built in to the atom orbitals. So when you have oxygen, right, or when you have this carbonyl, you'll have trigonal planar. When you have singly bonded carbons, those are all tetrahedral. And so basically you're connecting tetrahedrons in a lot of these structures that we've shown thus far. But I will tell you that once you have a double bond like this, you know, there's trigonal planar geometry when you have the double bond. And so you, in some cases, you need to break out your organic modeling kit and take a look at that. And because of that trigonal planar geometry, that's why you have cis and trans. And so it's easiest for now to look at the hybridization of the atoms. Carbon is sp3 in this case. And so it's going to be tetrahedron connected to tetrahedron connected to tetrahedron. And that's going to coil up the polymer chain and do other things we're going to talk about. So just like in organic chemistry, take a look at the functional group, figure out what the orbitals are like, and that gives you the geometry to start with. Great questions. Any other questions? All right, let's keep going. So my message is, don't forget the rules of organic chemistry. Polymers follow the same rules. And so you can write chemical structures however you want. Just make sure that your work is presented professionally, and I will try and be really clear, especially on exams, exactly what I'm looking for. But don't try and take too many shortcuts right off the bat, because if you try and do professional structures like this, you can get it wrong in a hurry, because counting all those carbons and getting everything just right is hard sometimes. My suggestion is to write everything out when you can, and then it's really hard to be wrong when you write all the atoms in. All right, great. Yeah, you know all about that. In general, there will be some mixed skeletal structure, especially when we have a functional group on it. And so make sure you know how that works, right? And where all the electrons are. There is no carbon right here, right? At the end of that point, because we have an oxygen atom right there, but the carbons are at the vertices, or the carbons are at the end. And what type of carbon or what functional group is this right here? What does that mean when we end a line? Yes. It's a methyl group. It's a CH3. So we can write out this molecule, and this is going to be a little bit tight, but I'll do my best here. O, H, C, CH3, CH3. What's wrong with this structure? What am I missing? Well, yeah, we can write the lone pairs in if you want. That's great, but we're really missing a hydrogen. And so remember, when you try and do this shorthand, remember that you get 4 bonds to all the carbons if I ask you to put all the atoms in. So that can be tricky, right? That can be a hard thing to do. Any other questions? Yes.
So I know in previous chemistry courses that when we're drawing those kind of writing out the actual skeletal structure, there's an actual orientation our professors wanted to do, like CH3, make it H3C or something like that. Would that matter if it's quartz? Or
I mean, I prefer that the covalent bond goes to the carbon, and then you tell me what's connected to the carbon. And so I really prefer like CH3 and then draw the line to the carbon. But as long as it's clear, I'm not picky. So just make it clear, make it look like the polymer structures in the book, make it look like the structures that I draw here, and we'll all be on the same page. Because polymers is really getting into materials and organic materials, and there's a lot of exceptions. There's a lot of different types of nomenclature for materials. There's a lot of it depends. And so we're getting away from some of the hard and fast rules that have been developed over, a long period of time, like organic chemistry. And you'll see a lot of different nomenclature and materials. So you're going to have to be okay with a little ambiguity sometimes. And once in a while, you're just going to have to dig to find the best answer, because materials can be a little messy. Polymers can be a little bit messy. Good. Any other questions? I see a hand. All right, great. We are all on the same page. I'll talk about aliphatic polymers. Those are saturated hydrocarbons or alkanes. I'll talk about alkenes and alkynes a little bit. Those are unsaturated hydrocarbons. You'll hear that term. And then aromatic, of course, is anything with an aromatic ring. I'll also call that a phenyl ring. I'll sort of mix my nomenclature a little bit because polymers are not perfect. And so if I'm saying some vocab words that you're not familiar with, just raise your hand and ask. It's no problem. Or write down that vocab word in your notes and say, I'm going to go look this up after class. All right. Okay. You know all about rotations. This one's important. And so this butane, yes.
I'm sorry, I actually don't know what aliphatic polymer is.
Yeah. So aliphatic is no unsaturated bonds or no pi bonds. So aliphatic is all sigma bonds. So if you look at this thing, this is an aliphatic molecule, all sigma bonds. And so alkanes are aliphatic because they have all sigma bonds. Alkenes and alkynes are unsaturated because they have some pi bonds. And then aromatic is a special case of unsaturation because you have aromaticity or you have delocalization around that ring.
Thank you.
Is that cool? Yeah. All right. Where are we? Where were we? Right here. Okay. So when we look at something like, what molecule is this right here? Don't be shy. 1, 2, 3, 4, 5, 6, hexane, right? And so this is just a linear aliphatic hydrocarbon, no double bonds, no pi bonds in it, no nothing. But this starts to look like a little short polyethylene, because even though we have a CH3 here, this is CH2 connected to CH2, connected to CH2, connected to CH2, connected to a CH3 because it's the N group. But polyethylene, because it has sp3 hybridized carbons that are all tetrahedral with sigma bonds, we get free rotation around those sigma bonds. So we can make this really long polyethylene chain and we get this free rotation around carbon-carbon single bonds. So this is like a very short chain of PE. And I'm going to start to use some abbreviations so you can get used to that. And if I write down an abbreviation that you don't know what it is, just raise your hand and say, I don't know what PE is. And I'm happy for the first couple of weeks to say it's polyethylene. You know, when we're at the end of class in the final and you're still asking me what PE means, I might be less inclined to answer freely. But now this is where the tetrahedral geometry comes in, because there's a tetrahedral or sp3 carbon here, there's one there, 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 and all of those carbons have this 109.5 tetrahedron. And so if you put this together with your organic chemistry kit, you'd see this chain really kinked up because of the tetrahedral geometry. There is no cis and trans when you have all sigma bonds because of this free rotation. So you can't have anything locked into a stereochemical arrangement. When you have double bonds, now you can have cis and trans arrangement of those double bonds because you don't have free rotation around this, because the pi bonds lock things into place. And so that's an important thing to think about. You know, that's, you can eventually try and get some rotation, but either the molecule is going to fall apart or it's really hard to do. So we say there's no free rotation around these double bonds. And that's what gives us a cis and a trans isomer. And you just need to make sure that you know that when I draw something like this is trans because it's across the double bond, right? And cis means the same side. And so these substituents are on the same side of the double bond. That is, well, it may be confusing because you're like, what does cis and trans really mean? I can't really connect it to like, hex is 6. I don't use those, that nomenclature very often, but just remember across and on the same side. All right. And once you have this molecular orbital, right? Once you have a double bond between carbon, we would idealize that as trigonal planar because there's only 3 substituents coming off carbon. And it turns out that it's not perfect. It's not 120 degrees. It's not perfectly trigonal planar, but now it's about 121.7 degrees. That's close enough to trigonal planar for us. And so the geometry, or whether it's trigonal planar or tetrahedral or whatever, is built in to how the atoms are bonded. And so remember, we have hydrogens here because we need 4 bonds to that carbon. We need 4 bonds to that carbon. This is a CH2. This is a CH3. This is a CH2. This is a CH3. And so we would have trigonal planar geometry here. We would have trigonal planar geometry at this carbon. And then we go back to sp3. So we've got tetrahedral geometry at all these other carbons. And so now you start to have some mixed geometry around different atoms. And you need to look at case by case basis. Walk down the backbone. What is the geometry around this carbon? What is the geometry around this carbon? What is the geometry around this carbon? And you start to piece it up that way. So it's not always as easy as polyethylene, where everything is just tetrahedral. You can have mixed sp2, sp3 when you get unsaturation. So remember that. Okay, all right, we got that. And so you'll notice when we did our example of polyethylene, you go from something that's unsaturated, unsaturated, alkene. And then when you make polyethylene, this is a saturated alkane or aliphatic, because you need these electrons in this covalent bond in order to make the connections here and here. Remember, there's 1 electron in each of those covalent bonds because we put the parentheses through it, which means that the monomer sitting right here next to polyethylene has also donated an electron into that covalent bond to connect the monomers. And so when we make these polymers like this, and let's go to the general case, we take, in general, something that's unsaturated or has a double bond, and then we make something that's at least saturated in the backbone or single bonded. And that's one of the real pieces of magic that you need to remember, is that it's okay if a double bond goes away if you can figure out where the electrons go. But we haven't gotten rid of any functional groups yet. We haven't gotten rid of any atoms. And so make sure that you can understand how that works. And the only way to really get it is to go home and practice it. I know you have nothing going on tonight, or probably nothing going on Saturday night. So break out your piece of paper, break out your organic modeling kit, and just get busy with chemical structures. That's what I'm going to be doing. All right. Any questions or comments so far? All right. We got tons of time. All right, cis and trans isomers, they exist when you have double bonds. And so don't forget that. We're not going to do a lot of isomerization, but just make sure you remember the general rules. And then when we do get to it, we will talk explicitly about isomers. So you don't have to worry too much about isomers yet. But when we get there, I will tell you. Just make sure you remember that. All right, great. Did that. Key is the hydrogens. this is a nice example. And so make sure you can understand what all of these bond angles are like and why they are what they are. And so we won't talk tons and tons about molecular geometry, but when we start to figure out how big a polymer chain is, you have to remember that there is a kink in the chain because of the tetrahedral geometry. But just, we're still in the review phase, so make sure you remember that. Okay, this slide is really important. And so this is where a lot of the jargon is going to come in. Remember, alcohol versus ether. Alcohol has an OH, and so it has an R group on one side, but it has that OH, that's the signature, where an ether has an R group on either side of the oxygen, and we got 2 bonds to oxygen, we're good to go. Amines, we have primary, secondary, tertiary amines, depending on the number of R groups. You should know that, remember that. And if you really want to draw the lone pairs, that's fine. But I will tell you, oftentimes, and even on oxygen if you want, oftentimes we don't draw the lone pairs in polymers because there's just too much going on. There's a lot of atoms and a lot of lines flying around, so you don't have to draw the lone pairs unless you're going to use them for something. Okay, hydrocarbon, yeah, okay, all that stuff, that's great. This slide is also important because this starts to get you from the really easy stuff that you learned in high school, hopefully, to the stuff you learned in your organic chemistry prerequisite for this class. And so when we talk about what acete is, or when we talk about an acid in polymers in general, we're talking about a carboxylic acid, and unless I tell you otherwise. Why is this called formaldehyde? What does form mean? 1 carbon. So methane, meth also means 1 carbon, but formaldehyde is from an old piece of nomenclature. And so form means 1 carbon, like formate, formaldehyde, that's got 1 carbon in it. Acetic acid, acete means 2 carbons. And so here's 1 carbon for acete. Here's the second one. And we might be tempted to say eth because eth also means 2 carbons like ethane, but we need to be able to switch back and forth between a couple different nomenclature systems. And so this is a nice cheat sheet to just print, put on your desk so you can refer back to it easily. Benzol has a benzene ring in it, and it's connected to an acete group, 2 carbons over there. What else is in here? There's other hard stuff in there, but you want to make sure that you know what amides are. We're going to make a lot of amides in this class. So nitrogen connected to a carbonyl. It's not an amine. It's not a ketone. It's an amide. Here is the ketone. Carbonyl group bonded to 2 different R groups. Carboxylic acid looks like a ketone, but it's got this OH group on there. And so that's not a carbonyl group connected to an alcohol. That is a carboxylic acid. An ester is a combination of what kind of looks like an ether connected to a carbonyl. It's not carbonyl ether, it's an ester. And so you're going to be accountable for describing polymers using this nomenclature, because when we say polyester, you can think polyester clothes, but that actually describes the functional group of the polymer. So when we write out polyester chemical structure, you need to make sure there are esters in there. Or nylon is the trade name of a polyamide. And so when we synthesize polyamides in this class, you need to make sure that you've got some amide functional groups in there. And so this gets to the next part of drawing chemical structures, making sure all the functional groups are correct. It's pretty easy to connect carbons, make sure we have the electrons, but accounting for some of these things will get trickier and trickier. So make sure that these are words that you're familiar with. And if you need to print a little cheat sheet and carry it around with you, that's fine, no problem. We're all learning. Questions, comments? All right. Great, we did all that already. So we're not going to belabor the organic chemistry. I mean, this is not an organic chemistry class, it's a polymer class, but we're going to use all the tools that you've already learned in your prereq to describe polymers. And so I know that you all loved organic chemistry, and there was probably just magnificent learning going on during that class. It's okay either way how it went for you, but we're not going to get away from some of those tools. I'm not going to grill you on SN2 and E1 and all that stuff, or give you really hard nomenclature problems. I'm going to give you pretty easy nomenclature problems like hexane, butane, things like that. But you can't be scared of the organic chemistry, because that is the only way that you can learn about polymers. And let's face it, polymers are a lot cooler than organic chemistry, so it's worth it. All right. So my polymer question is, which polymer do you think is more flexible? You can practice your clicker if you want. Oh, I didn't start the clicker. Forget about it. We will start clickers next week, I guarantee you. And I've heard that used clickers are only like 14 bucks downtown if you're interested in finding one at the bookstore. But anyway, which polymer is more flexible? You could shout it out. Let's say, who votes for polyethylene? Great. Who votes for polyacetylene being more flexible? Okay, why is polyethylene more flexible than polyacetylene? Single bond. So you have rotation around this single bond. Sigma bond equals flexible. Polyacetylene, you notice, has single bonds in it. So there's a sigma bond there, but there's a pi bond here. And so a mixture of sigma and pi bonds, but pi bonds restrict rotation, and that equals less flexible. Excuse my handwriting, but there is a video that's going to be posted of this. And so if you can't read something from the slide, just check out the video, because I will try and say what I'm writing down. And if you really can't understand what I've written on the slide, it's okay to say, I think that's wrong, or I can't understand your handwriting. But we'll get used to each other, and my handwriting might get better throughout the semester as I practice. We'll see. So why is polymer flexibility important? I mean, who cares? Why might a flexible polymer versus a non-flexible polymer, what can we kind of think about in terms of properties that might be interesting? Yeah. That's right. A flexible polymer chain might give you a flexible polymer material, and it does. It also gives you a low glass transition temperature material, which we'll talk about. And a stiffer polymer chain tends to give you a stiffer polymer material. And so if we compare a rubber bouncy ball, that's pretty flexible polymer. Or if we compare something like the case to this remote, that's a pretty stiff, glassy polymer. And this thing is a stiff chain polymer that goes into this remote, and our rubber bouncy ball has a nice flexible polymer in it. So we can start to connect what's happening with the molecules right to the properties on this slide. Yeah.
Is our very branched polymers typically, are they intrinsic, like, is a flexible polymer not branched, or can it be branched? Is an inflexible polymer branched, or can it not be branched?
Either. It really depends on the chemical structure. Branching, cross-linking, other things are different. We're going to really focus on linear polymers for a little while longer, and we will talk about cases of branching and how branching works. But for now, we're just going to focus on like the intrinsic linear polymer. What does it look like? Because you can always take a branch polymer and zoom in, zoom all the way in and say, okay, what is the monomer, and what is the repeat unit, and what is it doing? That's a start. And then you account for branching and cross-linking and other things like that. Good question. Any other questions or comments? Yeah.
I was wondering, like, how polyacetylene could meant to, or I guess, like where the name for that came from?
Yeah. So that is a different nomenclature again than acete, which means two in when describing organic acids and stuff like that. So acetylene is just the triple bonded 2 carbon small molecule, and ethylene is the same molecule only with the double bond. So it's a weird different nomenclature. Acetylene is the common name. I'm sure there's a scientific name that makes sense. I just don't know what it is. It might be called ethyne, right? Because it's a triple bond, so it's an alkyne, and then it's got 2 carbons, so F. And so, I mean, I could call this ethyne in this class, and you'd be like, okay, I get it. But if you go out and talk to someone on the street and say, hey, I've got this tank of ethyne, they'll have no clue what you're talking about. But if you say, I've got this tank of acetylene, they'll know exactly what you're talking about. Yeah, so that's a really good question because the nomenclature is mixed. And I want to get you used to all the different ways to describe these molecules, because we are not in the straitjacket of it has to be rigid like this. I want you to get used to the ambiguity sometimes. And I'll give you the straight story on the names most people use. And it doesn't always make sense. Yes.
So back on that slide where we're gonna go for the more or less flexible, what is the TG? What is that?
Yeah, so we're going to talk about that on the next slide if we get to it today, but it's the first thing we're going to talk about on Wednesday for sure. So TG equals glass transition temperature. And I'm going to have a lot of things to say about TG in the future. It's one of the thermal transitions that you're going to have to know to study polymers. And for right now, low TG means flexible, high TG means stiff. That's all you need to know. And we'll talk exactly about the definition of TG and why it's useful and how it's used and all that later. Any other questions? All right, we're getting there. You remember Newman projections? That's great. Remember that. All right. Which polymer more freely rotates? Yes. Yeah, so you guys are ahead of me for sure. So there is only a TG for amorphous polymers, but every single polymer has some amorphous fraction. And so every single polymer has a glass transition temperature without exception, whether you can measure it or not. Sometimes it's hard to measure because if a polymer is too crystalline, it's hard to measure the amorphous fraction. But no polymer is 100% crystalline, except if you make a single crystal, and then people debate about whether it is a single crystal or not. But no polymer is 100% crystalline, unlike a piece of steel. So if you have a piece of steel or a piece of iron, that thing is almost 99.99999% polycrystalline or a single crystal. So metals, ceramics, inorganic materials, you can get to 100% crystallinity, no problem. That's why those materials have the properties they do. But polymers in general are either all amorphous or a mixture of crystal and amorphous. So there will always be a TG, and we'll talk about that. All right, back to my question. Which polymer more freely rotates? A? Who votes for A? Who votes for B? Why doesn't B freely rotate? Go ahead.
There are interactions between the 2 metal groups.
That's right. So you have sterics equals less free rotation around sigma bond. Still the same backbone, right? Sigma bond here, 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 sigma bond here. It looks like you should get free rotation. Looks great, except those 2 methyl groups are going to bump into one another because what you know about Newman projections, right? All right, good. So which one has the higher TG? So you need to listen to me when I say lower TG, or higher TG? Which polymer on this slide has the higher TG? B. Why? Less flexible, right? Higher TG equals less flexible. So I'm not always going to ask you what's the lower TG or what's the more flexible polymer. I might ask you what's the less flexible polymer, which one has a higher TG. So you have to parse the question really carefully, especially if you have a multiple choice question like you're going to have on Canvas. I apologize for that, but you will get to demonstrate your expertise through the homeworks and the written part of the exams as well. But read the question carefully and answer the question that I ask. That is always a point of difficulty if you're not answering the question that I ask. All right, but you nailed that one. Great. Okay, intermolecular forces. There are some that are really important, and we talked about this last time. So dipole-dipole forces are higher than, we don't even have van der Waals forces on here, but you know that van der Waals forces are going to be less than dipole-dipole. So we have non-polar polymers. Like polyethylene. And then as we put polar functional groups in there, you get higher intermolecular interactions between chains, like if you put carbonyls in a polymer or something like that. So what would you guess if you have a non-polar polymer and then you have a polar polymer, all other things being equal, which one has the lower TG? Go ahead.
The polar.
Why would the polar polymer have a lower glass transition temperature? Remember, polar molecules are going to have dipole-dipole interactions, right? And dipole-dipole interactions are going to stick polymers together. So if I have a non-polar polymer, just van der Waals, they sort of, the chains float by each other. If I have a polar polymer, which one is going to have the lower TG? Non-polar, that's right. Non-polar stuff only has van der Waals forces, lower TG. Polar stuff has higher intermolecular interactions, and so you're going to have a higher glass transition temperature. And this gets to the inter and intra-chain interactions. We're going to talk a lot about that. Interactions between chains, interactions within chains. And so you're going to have to account for both sometime. But I will ask you explicitly to answer the question whether it's going to be, let's say, a question about rotation or a question about polarity and intermolecular forces. But remember, we've got both things working here. And we also have the special feature of polymers. When we take two polymer chains and they wrap around each other, what is that called? Entanglement. So when they wrap around each other, it's entanglement. When we make a covalent bond between them, that's cross-linking. Yeah, we'll get there. And so there's a lot of stuff going on in polymers that contributes to their properties, and that's what we're going to march through this semester. All right, we have hydrogen bonding. Just know how to identify that. I'm going fast because this is review. Okay, this is an important one, and I'm not going to do a clicker question on this because we're not starting clickers till next week. But identifying resonance forms is important because especially this is not a resonance form. Why is C not a resonance structure from one to the other? Go ahead.
Same molecule.
No, that's not it. So we draw it out. They are the same molecule, of course. That's fine. But what if we keep the orientation? Why is that not a resonance form? Yes. Well, you didn't move any electrons, and if you really wanted to change from one structure to the other, you could say, okay, I'm going to push these electrons over. But in order to make that happen, you'd have to move a proton over. And anytime you move a proton, it's not a resonance form. Yes.
Because the same molecule. We feel like those-
That's right. It's the same. So there's a couple reasons why it's not a resonance form. It's the same molecule. You know, you would have to move the proton if you wanted to keep it just right. but just make sure you're able to identify this stuff. We're not going to do a lot with resonance forms. This is just our organic chemistry warm up. And remember, arrow pushing, we've already done a lot of arrow pushing, but make sure that you really take a look at this slide and are able to account whether it's a full arrow, a half arrow. We're going to break bonds. We're going to make bonds. We're going to make polymers. Sometimes you're going to have some small molecules that are spit out when you make those polymers. And so make sure that you know how to do some arrow pushing. All right. We have 5 minutes left, so we're going to keep going. Any questions so far? Let's see. Is this number 3? I think it is. Okay, we'll cover that example next time. I want to keep talking about polymers for a second. All right, so there's a lot of things on this slide. This is what you want to start thinking about. I'm not going to read them off for you. You can read them off, but things like this, you know, check-in sheets or learning objectives or a list of basic concepts, and then you print the homework, then you look at the slides, and then you look at the book. If you start to integrate all those different things, this will tell you exactly what I expect you to learn from this unit. And we have nice compartmentalized exams in terms of section 1 to section 5. The final, I will break it to you now, is cumulative, so you can't forget anything. I'm going to ask you something about sp3 carbons on the final. So the stuff we talked on the very first day is going to be important, but the exams will not be cumulative. In general, they'll be confined to the section, but of course, you need to remember some stuff from the past. You can't forget about molecular weight and other stuff like that, or TG, because we'll use those concepts throughout. But I will try and confine how I assess you to exactly what the study sheet says, so you know what the major topics are. There's not going to be a lot of gotchas. Yes?
Will the final exam also be on Canvas?
Yes, the final exam will be remote on Canvas, but there will be a written part. It will look just like a regular exam, just longer. And that final detail will be posted by the registrar whenever they post the thing, because we have to declare it's a Canvas final. And so you'll see it in the final guide. And we'll talk a lot about that. I publish study sheets. We have extra office hours. And so I just talk about the exams and the finals so you know what to expect, but it's not something wildly different. It's not crazy. And we have ways to mitigate issues. Okay. So when we build up a polymer, we've been talking a lot about monomer. Oh, geez. Sorry about that. I'm going to sign in so it doesn't forget all of my notes. It's going to be a pain throughout the semester, I can guarantee it. All right, two-factor. Make sure no one's stealing my MATSE 202 PowerPoint notes. Okay, all right. So remember what we're doing here, though. When we draw something easy, okay, that's fine. If I can draw. Oh, give me a break. Let's try this once more. If not, I have a backup. Okay, so we've been drawing really shorthand, right? Carbon, ethylene going to polyethylene, right? But what we're really doing is we're connecting one monomer to another monomer, which makes a dimer, which then makes a trimer, oligomer, and polymer. Remember, oligomer is a few, trimer is 3, tetramer would be 4, and then poly is many. And so when we synthesize a polymer, we've got lots of different ethylenes hanging out, and we're building up that chain one by one. And so there's a lot of ways to build polymers. And so you can take a look at this slide and think about it this weekend, and also think about different ways to represent these chains. linear chains, we talked about the line representation of polymers, branched, and then finally cross-linked. And we'll talk about what all these things mean on Wednesday. Don't forget the homework. Don't forget the PLA before Wednesday. And I'll see you in a few days. Thank you very much. Oh, yeah, hold on one sec.